Now I will talk about how the aberration and the scattering limit the depth of the image in the brain tissue. So aberration and the scattering, like why they limit the imaging depth in the brain tissue. What is the problem? I'll talk about that. Say for example we are trying to take the image of the brain tissue. Here is the brain. So ideally the focus should be here. But due to the aberration of the tissue, we will see the focus here. And if you look at the shape waveform due to the aberration, this is the shape waveform. If we use the adaptive optics, then we can counter-measure the shape waveform and remove the aberration. So we can remove at least the aberration part. What about the scattering? If we look at this graph, in the x-axis is the wavelength, different wavelength, and in the y-axis is the attenuation coefficient, that is in per millimeter. If we look at the graph, that in the low wavelength the scattering dominates basically, and the attenuation coefficient is high here. But as the wavelength increases, the effective attenuation coefficient decreases, and we can see two windows here at around like 1300 nanometer. We can see that both the scattering reduce and overall the attenuation coefficient decreases. What does that mean? If the attenuation coefficient decreases, we will be able to image in larger depth. And also another window is around here, around 1700 nanometer, and also here the attenuation coefficient also low. So these are the two effective window we can use to image in depth. So here is two example. If we send the light with low wavelength, so this is for low wavelength. So for low wavelength, low lambda, as we know that from the previous graph, that for the low lambda, we can see from this graph that, say for example, low lambda, we are sending light around like 800 nanometer wavelength. That means attenuation coefficient will be high. If the attenuation coefficient is high, then light will not be able to penetrate much here. So imaging depth will be low. So for the low wavelength, imaging depth is low. When lambda is low, the imaging depth is low. What about the higher wavelength? If lambda is high here, so lambda is high here. If lambda we increase, that means the laser source that we are using, if we increase the center wavelength, say around like 1300 nanometer or the 1700 nanometer, that means the attenuation coefficient they will experience while traveling into the tissue will be low. So weaker attenuation coefficient will increase the depth. So depth will be increased too. So if you want to take the image with depth, then we have to increase the wavelength of our laser source. So that is the requirement, because this curve determines everything. Because here we can see that attenuation is dominating at low wavelength, and around this point and this point we can see that effective attenuation coefficient is low. So that are the things we need to take care of, and also eventually we have to take care of the aberration of the wavefront by using the adaptive optics. Thank you very much.